What is it? What's the Hardy literal maximal function? You have some function, start off with some function, and it's locally integrable. Start off with some locally integrable function. And then you create this thing called a Hardy literal maximal function, and in book they denote it by F star. So you define MF or F star, the Hardy literal maximal function of F by what? What do you do? MF at some point is defined to be what? The supremum of all.
You take balls around X.
That's right, you take balls centered at X, and sometimes you take cubes, it doesn't matter. Cubes with sides parallel to the axes, but the results will be the same. So ball be centered at X. Okay, and then you take the average, right? You take the average over each ball of the absolute value of the function, right? So you take the absolute value of the function, integrate that thing over the ball, and then you divide by the measure of the ball. Divide by the measure of the ball, and you take, so that's the average of the absolute value, right? And then you take the supremum over all those things. You get the largest average. Okay. So you may know that Hardy was an avid cricket player and cricket aficionado. This actually, from what I hear, this actually occurred to him when he was trying to make some way of evaluating cricket players. So like you have a cricket player and he's having a season, and maybe his season was pretty bad at the beginning, but it's good later on. You know, how do you evaluate the current ability of a cricket player compared to other cricket players, right? Well, so he said, well, you don't want to average over the whole thing because right now he's actually doing pretty well, right? Or at least in the nearby time he's actually doing pretty well. So here's the nearest time. And he said, well, let's just average backwards over all possible intervals and see which interval gives you the greatest average, and that will be sort of like the current value of the cricket player. Okay, and this gave rise to the Hardy literal maximal function. So I've heard. Okay, so turns out that we're going to show later on that M is bounded on LP, P between 1 and infinity, right? Of course, if you're looking at its behavior on L infinity, then it's clearly going to be bounded, right, with bound 1, right? Because if you take an L infinity, a bounded function, and you take averages of the bounded function, it's still going to be bounded, right, with the same bound, right? So it's clearly bounded. So obviously, M is bounded on L infinity. However, when you look at L1, what happens? At L1, what happens? Well, it's not bounded, and it's not bounded. Right? Right? And the way you see that is by, for example, taking the characteristic function of 0, 1. So if I have the characteristic function of 0, 1, right? And then you see, like in R1, right, the maximal function is going to look like, right, if you're at X, the maximal average you're going to get is going to be over this ball, right? So your maximal function. The maximal function of this characteristic function is basically like 1 over x, right? And so it's not integrable, right? So you've taken an integrable function, but its maximal function is not integrable, right? So it's not bounded on L1. Okay. But however, although it's not bounded on L1, it does satisfy the so-called weak type inequality. Weak type inequality. Right? So however, M it is not that bad. satisfies a weak type inequality, a weak type inequality. That is to say that if you look at the place, you look at the set where the maximal function exceeds some height alpha. Okay? That is for each, i.e., when we say this weak type 1-1 inequality, we mean that for each alpha greater than 0, if we look at the measure of the set where the maximal function is great, then that's actually controlled by some constant over some fixed constant over alpha times the L1 norm of f. Okay. So the place where the maximal function is big, right? The place where the maximal function exceeds alpha is controlled by 1 over alpha times the L1 norm of f. Okay. And so this is called the weak type, weak 1-1 boundedness. So you notice, right? If M were bounded on L1, if we're bounded on L1, then we have something like this. We have like that you have that the maximal function's L1 norm is controlled by some constant times the L1 norm of L, right? Right. That's what being bounded on L1 means, right? And then you'd say, well, if we look at the size of the set where the maximal function exceeds alpha, right, and multiply that by alpha, then that's bounded above by the L1 norm of the maximal function, right? Because here, this thing, what's this? This is the integral of the absolute value of the maximal function. Okay? This is the integral, and the maximal function is positive. It's the integral of the maximal function, right? And that's going to be bigger than if you look at the set, that's going to be bigger than integrating the maximal function over this set, right? The place where the maximal function is bigger than alpha. Right? Could be just integrating over a smaller set, right? So let's say we're only going to integrate this guy over the place where it's bigger than alpha, right? And this is going to be bigger than, the function is bigger than alpha there. And so we recover the measure of this set, times alpha, right? So the measure of this set times alpha is controlled by, is smaller than this, is smaller than this. And so you see that being bounded on L1 in a strong inequality, the strong boundedness implies the weak type boundedness. Okay? Right? So that's the point here. Right? And this thing that we're writing here, this thing that we're writing here, or this thing here, this inequality here is also called Tchebychev's inequality. Right? You know, it's where you place for an arbitrary function phi, right? Alpha times the set where phi exceeds alpha is controlled by the L1 norm of alpha. Okay? So by Tchebychev's inequality, you see that strong boundedness implies the weak type boundedness. Okay. So everyone? You've all seen many of these things. Okay, so the weak type boundedness, right? Actually, one way of proving the boundedness of the maximal function on between 1 and infinity is to use an interpolation theorem called Martin-Cambridge interpolation. So that is, it allows you to interpolate between this weak type result, the weak type 1-1 boundedness and the L infinity boundedness, and that will give you the LP between 1 and infinity. Okay. The idea of the interpolation is actually sort of in the proof. So we're not gonna maybe later I'll state the interpolation formally, but we won't use Martin-Cambridge interpolation explicitly. In any case, the idea of the proof, I think, is in the proof of in the proof that we're going to see. Okay. So Martin-Cambridge was a student of Zygmunt. Zygmunt is sort of the king of harmonic analysis. Zygmunt is the advisor of Stein and Calderon. And the field of harmonic analysis that this book is linking constantly to is the so-called Calderon-Zygmunt harmonic analysis. So Martin-Cambridge was another student of Zygmunt's, an early student of Zygmunt who died in World War II, sort of tragically. Those of you who've had me before know the story of Calderon. The story is that Zygmunt was invited to teach down in Argentina for a summer, and he went down and was teaching his class out of his classic book, Trigonometric Series. And while he was giving one proof, there's a student there, and the student says, "Professor Zygmunt," the student is clearly getting irritated. He says, "Professor Zygmunt, that is not how you prove the proof, and that is not how you prove the theorem in your text." And Zygmunt thinks about it and says, "No, that is how I prove the theorem in my text." And the student says, No, you actually proved it in a much more elegant way." And he sketches out this proof. And then Zygmunt realizes that Calderon has not read his book in the normal sense. Calderon only reads the first line of each proof, and then figures out the proof by himself after that. So he started off in the same way as Zygmunt, but then found some much better way afterwards. So he invites Calderon to be a student of his, to come to the US and be a student of his at the University of Chicago. And 1 year later, Calderon gets his PhD, having produced 30 papers that are sort of revolutionized various fields of mathematics. So set your sights on it. Anyway, so Calderon is, this field is called Calderon-Zygmunt harmonic analysis. And Stein is one of the greats in it as well. Anyway, so let's get the weak type inequality. For M. So to do that, we need what's called the Vitali covering lemma. I should say that although there are people who call this the Vitali covering lemma, there are other people who say this is not the Vitali covering lemma, and will argue about it. So this is a corollary. This is called the Vitali covering lemma. Okay. So it's sort of a funny thing, but when you're trying to get boundedness of these maximal operators, often what you need is a corresponding covering lemma. So much so that I sort of feel that a lot of my graduate career was, a lot of my and my peers' graduate career was spent trying to prove covering lemmas, like just dealing with balls and rectangles. They're just thinking about balls and rectangles all the time. That's. I talked with a classmate of mine from those days, and he said, "What did we get out of those days? It's mainly how to do covering lemmas." Okay, so covering lemma. Can anybody tell me what the covering lemma says? What's the idea of the covering lemma? you have a bunch of balls. What do you do?
In order to make a new disjoint.
Exactly. Yeah. So you want to get a disjoint subcollection of those balls, but you want that, you don't want to be too picky about it. You want that disjoint subcollection to cover a certain fraction of the original area. Given any collection of balls, you can always make a disjoint subcollection. Just choose one, right? That's a disjoint subcollection, right? But you'd like it to be guaranteed to cover a certain percentage of the original area, and that's what we do. Okay. And you'll see why we want them to be disjoint in a second. So given a finite collection of balls, B1 to Bn, there exists a subcollection, Bij, such that when the Bij of this joint, Bij of this joint, and two, the sum of the areas of Bij exceeds 1 over 3 to the b times the area of the individual. So disjoint balls cover a certain. You can choose it in such a way that they always cover certain fractions. Okay, so what's the proof? The proof is sort of the one that you might think, you might guess is, if you're told to create a disjoint subcollection that covers, as much area as possible, right? What are you going to do? Let's order the balls in terms of decreasing radius. Order the balls in terms of decreasing radius. So I should say this is maybe the simplest of the covering lemmas. There are more sophisticated covering lemmas that give you sophisticated results about other maximal operators. So this one is pretty straightforward. Order the balls in terms of decreasing radius, and just choose the biggest, right? Choose the biggest, B1 as your first. And then, what do? You just look down the list and try to find the next one that doesn't intersect, right? Choose B2, find the next ball that doesn't intersect, B1, right? So we call that. I'm going to call it B1 tool. Okay. Call that B2 tool, right? And then continue, right? So you just if the ball intersects any of the guys you've already chosen, don't include them, throw them out, right? And then keep on going until you find one, that doesn't intersect the guys you've chosen, and then put that guy in, right? And then just keep on going until the end. Okay, so, right, and then continue until the end. Okay. And you say, okay, well, you notice that if a ball Bj, say, was not chosen, then it must intersect a chosen ball of greater radius. Right. It's not chosen, you must intersect somebody who is higher up on the list. Right? That means the guy has greater radius. But then in that case, the threefold expansion of B contains Bj, right? Contains the guy that wasn't included. Right? You have some ball, and this is a selected guy, Vitali, right? There's some other ball that was not selected. Well, that guy must be of lesser, equal or lesser radius. So if you expand this guy, 3 times, expand the chosen ball three times. Oops. Yeah, threefold chance expansion of B will contain the guy that you didn't choose. And so that's basically it. Right? You get that the size of the original collection, right? You get the size of the original collection, right, that these guys are all contained in the expansion, the 3 times expansion of the chosen guys. Okay, so sorry, I'm sort of switching notations. Let me put a 3 on it to say the 3 times expansion. Okay. The 3 times expansion of the original guys, right? And you know that is, so you know that this is smaller than that, right? Which is smaller than 3 to the b times the measure of the non-expanded guys, right? Times the measure of the non-expanded guys, right? But that is, that's what you want, right? Which, so these guys are disjoint, right? So you get the summation of the j, right? And so you get the subcollection. You get the subcollection. The area covered by the subcollection, is greater than 1 over 3 to the b times the area of the original collection. So pretty simple. Okay. So this is the Vitali covering lemma. Okay. And then so from here we use the Vitali covering lemma to get the weak 1-1 boundedness of M. So composition. For all that exists constant, exists a constant A, such that for all alpha, the size and set for the maximal function exceeds alpha, is controlled by A over alpha times the L1 normal F. do it? Should I let you think about it? Why don't you think about it? Okay. Think of, you're trying to control the size of this set. Trying to control the size of, this is pretty, this is, I think, pretty straightforward if you think about this, how it's everything. Try to control the size of the set, right? And so let's consider this set is the set where the maximal function is always bigger than alpha, right? So that tells you that for each point in the set, there's a ball centered there, right? Where the maximal function, is bigger than alpha. But that is, the average will be bigger than alpha. So think about it a little bit. It's not hard, and some of you have even seen it before. So. Oh, and so what? Just one thing to make it simpler. Take K, any compact subset of E alpha, and then you prove the thing for any compact subset, and then that will give it to you for the sets. You need the compactness for to take a finite subset. I feel like we're the only ones on campus. Okay, so let's think about it. What are we going to do? You've got this compact subset of E alpha. Right. Yes. Chen, what book do you have there? What book is it?
Analysis.
From Stein?
Huh?
Real analysis by
Stein.
Stein. turn to somebody, talk to somebody nearby. Talk to somebody in your area.
And then never stop.
So you can use
Okay. Would somebody like to say how they're thinking to do it? So let me just make the first move, right? K is a complex subset of E sub alpha, right? You know that any point in E alpha, you can cover every point of K with a ball, such that the average over that ball exceeds alpha, or it's greater than. Right? And then you take a finite subnumber. Take a finite subnumber B1 to Bk, or B1 to Bk. Okay. And then you notice that, well, what do you notice? On each ball, right, you see that you have something like the weak type inequality. Right? You have that the size of the ball is actually controlled by 1 over alpha times the integral of b of f over that ball. Right? So if these balls were disjoint, that would be great. Right? If these balls were disjoint, then you would just take the sum over the left side, and that would give you something that controls the size of K, and then on the right hand side you'd have the L1 norm divided by alpha. Okay. So but you don't have disjointness. Too bad. However, we do have the Vitali covering lemma, so we can pass to a disjoint subcollection. So use the Vitali covering lemma to pass to a disjoint subcollection. B triple J. And you say, okay, well then, we know that for each of these guys, B twiddle, each of these guys satisfy this, right? And you just sum over all of them. You sum over all of them, right? You get the and you know by the Vitali covering lemma that the sum of these areas exceeds that constant times the measure of the original divisional collection, right? And you know that that thing controls the measure of K. Over here on the right-hand side, you get 1 over alpha times the sum of these things, but that's, since these are disjoint, that's just going to be the integral over the union of over the balls. So by disjointness. And so that gives you 1 over alpha times the, that's controlled by the L1 lemma. Pretty simple. Okay, everyone all right? Eric, you're the one who hasn't seen this before. Is it okay? Is there any place funny or? So, right, you cover them with balls, you can find a subselection that still covers the complex set. Right? You notice that, on each of these balls, we basically have the result that we want. If only we could sum these things together, that would give us the result we wanted. We can't, because they're not disjoint. Right? It doesn't work. It would work if they were disjoint. But fortunately for us, we can use the Vitali covering lemma to pass it to a disjoint actual disjoint subcollection, which, and this is key, captures a certain portion of the original area. So, right, so that because it captures a certain portion of the original area, that gives us a bound on the set. So it's like it only works on part of the set, but that's okay. Right? All you want is a bound on the size of it. And so since we've done it on some portion of the set, we can get a bound on that fraction times the area of the set. Yeah.
Why Vitali chose 3?
Oh, I mean, you can probably do a little bit better, but it's just that if you so you have this ball, right, and it's intersecting another ball, right? You need to expand your radius 1 to 3 times to make sure that you are going. You need to expand the radius 3 times to make sure that you cover anybody of smaller radius who intersects you. Right? If somebody intersects you and they're basically the same radius, right, how far do you need to extend? You need 1, 2, 3.
So at least 3.
It has to be 3. Okay. So that gives us the weak type result, weak type boundedness of the maximal function. And so now let's get the LP boundedness. To get the LP boundedness, we need a result about the distribution functions. So let me put up a definition here. You have some function, so f is a non-negative measurable function. And we define, let me use capital letters because they use capital letters in the book. We we define the distribution function of f, so lambda of f, by lambda of alpha, so alpha is equal to 0. Lambda of alpha is the size of the set where the function exceeds alpha. So we've already basically been talking about the distribution function of the maximal function of f. Okay. And we're so okay. So in the next chapter we'll be talking about something called distributions. That's something completely different from the distribution function. So don't get confused. So what we need is the following lemma, that for p between 0 and infinity, the LP norm of the function equals the integral, the p power of the LP norm equals the integral of lambda of alpha to the 1 over 2. This could be sort of obvious to you, I'm not sure. So for example, for the case of p equals 1, it says that f, the L1 norm is just the integral of the distribution function. Right? You take the function that gives you the size of the set where the function exceeds that value, and you integrate that value, and that gives you the integral of the function itself. Okay. That may be sort of intuitively clear to you. Let me just prove. I'll just prove it in this one case. So the proof in case p equals 1 is just done by Houdini's theorem. Let chi be the characteristic function of the set x alpha in Rd plus R plus, where f exceeds alpha. And then, if you integrate it first, and so let's consider this thing over Rd plus R plus. If you integrate it first, if we write the alpha and the x, you see that what we get is right, alpha is going to go from 0 to f of x. Right. And if you integrate dx alpha, you see that you're going to get the measure of the set. You get the measure of the set where f of x exceeds alpha. Alpha and 0 to 10. Right. And so here you get Rd dx, you get the L1, you get the integral of f, and here you get the integral, of the distribution function. So just like Houdini's theorem. And then the other case is not all that much different. So let me Okay, so now let's look at the theorem. Let's suppose that f is an LP for p between 1 and infinity. And our claim is that the Maximal function is bounded on LP. Okay, so we're going to break this into two parts. Well, we're going to do this in two steps. Our first claim is that just that the maximal function is finite. So for f in LP, the maximal function is finite almost everywhere. And this is maybe if you've read it, does anyone know how we do this? Did anyone read the proof of this? The trick is to do a splitting of the function. Right? So you take the function, you let f1 be the function where the function is large, and 0 where the function is small. And then you let f infinity be the opposite, right? So it would be 0 where the function is large, and it'll be f of x of s. So you break it up into the parts where it's bigger than 1, parts where the absolute value is bigger than 1, and the parts where the absolute value is smaller than 1. Say, okay, then you say, well, look, f is f1 plus f infinity, mf is bounded by m of 1 plus m f infinity. Right? Because the maximal function is sublinear. Right? Okay. Well, what can we say about what can we say about this? This is smaller than 1, right? It's smaller than 1. And what can you say about this? Well, right, we're trying to show that this thing is finite everywhere. So, right, well, it would be great if this thing were finite everywhere, right? Because that would be done. So why is this guy finite everywhere? Well, what do you know about f1? f1, the function f is an LP. Function f is an LP. f1 is the function where the function size is bigger than 1, right? So when you take it to the pth power, it will only grow bigger, right? So that's to say that f1 is in, right? F is an LP, f1 is actually in, well, right? f1, we know that function and raise it to the p power, it only gets bigger, right? So you have this, right? Okay. So that tells you that the integral of f1 is controlled by the integral of fp, but that's fine, right? And so f1 is an L1. Well, f1 is an L1, so that tells you that mf1 satisfies this this weak type. Is a weak, right? Has this weak type inequality, right? So we know that the size of the set where mf1 is bigger than alpha is controlled by the L1 norm of f1, right? And so that tells you that the size where that tells you that mf1 is finite almost everywhere, right? Okay, so that gives you that mf is finite almost everywhere. Okay. Is this boring? I don't know. Is this boring? It's not boring. Okay, good. You look bored. Or maybe I feel a little bored. But no, I feel like you guys look a little bored. I hope you guys, I feel like this at least a little bit. It's not that exciting. But we're heading, we're heading towards, this is all setting us up for really important stuff. So it's good. Okay, so we get the first thing, that the maximal function is finite almost every, right? For functions in LP, the maximal function is finite almost everywhere. Okay. And then we combine the L infinity. We already know we have the L infinity bound, right? And we're going to combine the L infinity bound with the weak bound to get the LP bound. And so this is sort of hinting that one might be able to do this in general. This is the idea of Tchebychev interpolation. So here's what we do. So part 2, LP boundedness. Okay. So now we split the function again. We split f again into f1 plus f infinity. But this time we do it a little bit different. F1 is going to be f of x if f exceeds an alpha. So it'll be dependent on alpha. So guys, really, what I should say here is sort of like an improved weak type inequality. That's what we're going to do. That's what we're going to get to get the LP boundedness. Okay. And 0 otherwise, and as before, infinity is going to be the opposite. 0 if f exceeds alpha over 2, and f otherwise. Okay. Again, observe that, as before, the maximal function is controlled by mf plus nf infinity. That is to say, it's controlled above by mf1 plus alpha over 2. So what does that tell us? That tells us that the set where the maximal function exceeds alpha, if the maximal function exceeds alpha, that forces the maximal function of f1, to exceed alpha over 2. Right? If this guy is bigger than alpha, if this guy is bigger than alpha, then certainly this guy is bigger than alpha over 2. Subtract alpha over 2 from both sides. Okay. Using now the weak type inequality, we see that this gives us, this tells us something about the, this tells us something stronger about the distribution function of the maximal function. Okay. Right? That this set is controlled by the size of this set. Right? And applying the weak type inequality to this guy, we get A over alpha over 2 times the L1 norm of NF1. I'm sorry, the L1 norm of F1. Right? Well, the L1 norm of F1 is the integral of F over the set where F exceeds alpha over 2 Maximal. Right? So we get this result here. The size of the set where the maximal function is bigger than alpha is actually bounded from above by this sort of result. Right? We're not getting, it's a little bit better than the L1 norm. We're not integrating over the whole space, we're only integrating over the space where the function is larger than alpha over 2. I'll leave that up here. This thing is the distribution function of the maximal function. Okay. Everyone all right? Pretty straightforward. Should probably stop saying that. It's probably gets that nervous. Keep on saying it's simple. It's easy. When I first started teaching, there were 2 professors who were assigned to watch over me, and they said, "Stop saying trivial so much. Keep on saying that everything is trivial. Stop saying that." But it's 20 plus years later, and I'm still saying it. Okay. So let's finish it up. So, using the lemma, the distribution function lemma, we see that the function to the pth power is bounded by the distribution function alpha to 1 over p d alpha, right, which we just got bounds on. Right? We see that that is going to be integral from 0 to infinity to a over alpha to 1 over p, the integral of f over the set where f exceeds alpha to 1 over p over 2 d alpha. And then the rest is calculus. You change the order by convenience theorem. okay, this is going to be equal to 2a 0 to infinity. Oops, so we're changing the order. RB f of x, the integral from 0 to 2f x to the p, 1 over alpha to 1 over p d alpha dx. And then you just integrate that, and you get some constant, which I'm just going to call AP, RD f to the p minus 1 dx. But that's, of course, the LP norm of f to the p. Right? And so you get that. So you get the bound. Okay, so it's complex. Okay, so the real key is this one right here. This is the hard one, right? That you can, if you have the L infinity boundedness and the L1 boundedness, you can incorporate the L infinity boundedness into the L1 boundedness and get this strengthened L1 boundedness. That strengthened L1 boundedness integrates to give you the LP boundedness. So this is really the heart of the thing here. Any questions? Let me start talking a bit about Hardy space. We've been introducing the Hilbert transform and the maximal functions. These are sort of like the key. These are prototypes of the key concepts in analysis. Hardy space is sort of like the place where these guys behave nicely, where these sort of characters behave well. It's the setting for them. Okay. So the point is that as we're seeing, L1 is not such a good space for these things, right? The Hilbert transform fails on it, right? Doesn't have LP boundedness, L1 boundedness. Maximal function also fails to have L1 boundedness. Okay. There's a space that is sort of like a replacement space for the endpoint. As p goes to 1, and there's a dual space. It's dual. The space of space called BMO, bounded mean oscillation functions. So there's a Hardy space. There's a bottom space that serves as a replacement for L1. Its dual BMO serves as a sort of replacement for L infinity. And it's on these spaces that singular integrals and maximal functions and the like behave well. So the funny thing is that the Hardy space can be introduced in multiple ways, some of which are purely complex analytic, and some of which involve sort of really complex. You create these things called the grand maximal functions, and then you define the Hardy spaces. Those functions in L1 on which the grand maximal function is bounded. But Stein chooses to define Hardy space in terms of the atomic decomposition. Okay, so this is sort of a bold move. So here, let's do it. I think this is maybe the simplest. It certainly is maybe the simplest way to introduce the space. Okay, so we will introduce the space in terms of its atomic decomposition. So this is historically backwards, right? Historically, you introduce the space. The space was created first, and then much later on, people found it has an atomic decomposition. Okay, which was like a great result. But now we're taking the atomic decomposition as the definition. Okay. So, the atomic decomposition definition of particles. That just seems, just writing that seems wrong to me, because normally you have the definition of Hardy space, and later on you say, lo and behold, you get this atomic decomposition. Okay. So first we define these things called atoms. So let A, funny looking A, let A be a bounded, measurable function on Rd, and B be a ball in Rd, and if the support of A is contained in the ball, 2, the function is bounded by 1 over the measure of the ball, and 3, the integral of the function is 0, so it satisfies the cancellation. Right. The second thing is like a size condition. Right? You notice that that forces the L1 norm to be 1, right? To be smaller than 1. If these things happen, then we call A an atom associated with B. Okay, so it's an atom living on the ball B. Okay. Okay, so now let's define a Hardy space. Suppose you have some function in L1. If there exists Lk, so if there exists a sequence of numbers, Lk, and a sequence of atoms, Ak, sequence of scalars, and again, a sequence of atoms, such that F can be represented as this as the sum of these guys, and such that if there exists a sequence of scalars such that the little L1 norm is funding, and a sequence of atoms such that F can be represented as this combination of the atoms, then we say F is in the real Hardy space, H1. Usually we just call this the Hardy space. And further, and we define the H1R norm as the infimum of all of these little L1 norms of the sequences. The infimum of all these things over all such decompositions. Okay, so this is over all, you look at all possible ways of representing your function as atoms, and and you look at the coefficients that give you the smallest little L1 norm, and that's defined to be the Hardy norm, the H1 norm of F. And so, Stein makes some observations that he leaves you for homework. First, and I'm not sure if I'm going to assign it, but first is that H1 is complete. So it's a Banach space. Two, if F is in H1R, then F satisfies the cancellation condition. And third, that the H1 norm is bounded below by the L1 norm of the function. So next time, we are going to show that, so next time we're going to show that if F is now P and F has bounded support, then F is in H1 if and only if F satisfies the cancellation. And the way we'll do this is by using something called the Calderon-Zygmunt decomposition, which I think I might have mentioned earlier as being the result throughout history that I would plagiarize. Did I mention this story? Yeah. So next time we'll see a variant of the great Calderon-Zygmunt decomposition. Wait, next time no, there's an exam.
Yeah.
Next time there's an exam. So next time there's an exam, but the time after that, we'll see the Calderon-Zygmunt decomposition.